Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving a very nice quintic equation with complex numbers. So we have z to the power 5 plus z to the fourth plus 1 equals 0. Wait, oops, I meant z to the fifth plus z to the fourth equals -1, and then we're going to be solving for z values. But of course, we're going to add 1 to both sides so that we can make it a polynomial equation in standard form, and then we're going to proceed from there. Okay, so let's go ahead and take a look. Now, I don't know if this problem can be solved in more than one way. I believe so. I'm just going to show you a method that I really like, and then which is something that doesn't always work, by the way, and then I'll show you an alternative approach. Okay, let's go ahead and add 1 to both sides first to get our full quintic. Even though I say full quintic, it's not a full quintic, it's missing a lot of powers, but that's a good thing. We don't have z to the third, z to the second, and z, we only have these powers. But that's okay. So we're gonna go ahead and manipulate this equation in a way that it's kind of factorable, right? So to be able to do that, since a lot of powers are missing, this shouldn't be too hard. And one of these methods, by the way, is gonna be incomplete because of the the complexity and the length, but hopefully you can just go ahead and finish that up, right? So here's my approach. I want to go ahead and factor this expression. That's because that's basically how I can find the roots, right? But wait a minute, isn't this like a quintic? Yes, it's fifth power, so there's actually a couple different ways this can work. We can factor it into a quartic and a linear polynomial. That wouldn't be super helpful because then you would have to solve the quartic. Maybe instead of that, why not try a cubic and a quadratic? 3 plus 2 is 5, right? So, and since this is monic, the coefficient of z to the fifth is 1, I'm just going to assume that this can be factored as follows, okay? Something like this. This can be factored into z squared plus az plus b, that's going to be my quadratic factor. And the other factor is going to start with z cubed so that we can get the z to the fifth. Notice that they're both monic. And then we have to continue with c. We don't know what's going to happen. Maybe we can adjust it later and just say, okay, this will continue with cz squared plus dz plus e. Now, here's one thing that might make this problem a little easier. The constant is 1, so you can make an assumption and say, hey, b and e are either both 1 or both -1. And you can go with both cases and see if that works. If that doesn't work, that means we're in big trouble, because in that case, you're going to find some irrational numbers, because that doesn't necessarily mean all the coefficients of integers, but that's very likely. And as you will see with the other method, that it should work. But that's basically the idea, right? If you go ahead and distribute, now notice that there is no z cubed. And just think about, where does z cubed come from, right? Z cubed can come from z squared times dz, az times cz squared, and 1 times z cubed. So there's 3 ways it can come up. What about z squared? Z squared can again come up with a couple different ways, so we kind of have to consider all of those cases. But let's go ahead and do this. Z to the fifth is not going to make a difference, so let's go ahead and start with z to the fourth. Well, how do you get z to the fourth from here? Z squared multiplied by cz squared, that's cz to the fourth. And then to get another z to the fourth, you can multiply az by z cubed, which is going to give you az to the fourth. And then what else? We don't have z to the fourth in the second one, so 1 times anything will not give you that. That's pretty much it. So this needs to equal 1z to the fourth, which means c plus a is equal to 1. So that's one equation you need to keep in mind. Cool. I'm going to do it power by power, so it's a lot easier, so I don't have to use the distributive property like crazy. Now, where does z cubed come from, right? Z squared times dz, so that's dz cubed. And then with the az, I have to multiply by cz squared, so it's going to be acz cubed. And the last z cubed is going to come from here. You've got to be very careful with that. And of course, we don't have any z cubed on the right-hand side, so that's going to become 0z cubed. Make sense? So this means d plus ac plus 1 is equal to 0. That's just another equation you need to solve. We have a, b, c, d, 4 variables. If you can come up with 4 equations, which we can, you should be able to solve it, right? Hopefully. Now, the next thing we're going to look at is z squared. the coefficient of z squared on the left-hand side is 0. On the right-hand side, z squared times 1, that gives us z squared. And then we have az times dz, which is ad z squared, right? Are there any other z squared? Let's check. 1 times cz squared. Yes, the last one. C z squared equals 0, right? Well, or you can write this 0z squared, and then just think about the coefficient. 1 plus ad plus c is equal to 0. That just gives us another equation. Notice that there is some similarities between those two equations, right? And then the next thing we're going to look at is the coefficient of z, and then finally constant, but constant is always taken care of. Like I said earlier, if this setup doesn't work, you can try -1 and -1, and if that doesn't work either, then you're in big trouble. You're going to have to kind of do it differently, okay? Or just solve the system with more variables. Who doesn't like that, right? So to take a look at z, again, we don't have any z on the left, so coefficient of z is going to be 0. Az times 1 is going to give us az. And then are there any other z's? Yes, if you multiply 1 by dz, kind of makes you dz, doesn't it? It's going to give you 0z, which means a plus d is equal to 0. I think this system is solvable because notice 1, 2, 3, 4 equations and 4 variables. So good luck solving that because I'm going to proceed with the second method. Don't hate me for that, okay? I'm going to leave that as an exercise for you guys so that you get to exercise your skills, right? Okay, great. Let me know what you find from solving that system. And now we're going to look at the second method, which is actually my favorite. But again, with caution, this method does not always work. Okay? Only for certain situations. But most of these problems, most problems on my channel, by the way, are competition level problems. Some are Olympiad problems. Some have appeared on IMO, AMI, USAMO, USAJMO, whatever, you name it. AMC 8, AMC 10, AMC 12. I also provide training for those in case you need one-on-one tutoring. I also provide that, and I'll probably come up with a platform so you guys can apply. Anyways, that's a different story, but just trying to tell you that for these problems, there's usually a quick, slick trick, okay? So how does that work? So if you know certain polynomials, then this will be a lot easier. But let me show you that. So I'm going to go ahead and subtract z squared from this and add z squared to it. So if I subtract and add the same thing, does that really change anything? No, not really. So it's okay. But you might be questioning, like I know some people are going to say, why on earth you're doing something like this? The reason is simple, not that simple, but kind of simple. This makes this expression factorable. We can factor both of these, and guess what? They're going to have, okay, let me now spoil the surprise. I'm going to factor out z squared. That gives me z cubed minus 1. And this expression actually can be written as z to the 4th plus z squared plus z squared plus 1 and then minus z squared. What I did here is basically I added z squared and then subtracted z squared, which is again okay, right? Because these two will cancel out. Great. But why did I do that? Because if you look at this carefully, first of all, z cubed minus 1 is difference of two cubes. So it's factorable, right? And then this expression is z to the 4th plus 2z squared. 2z or not 2z, again, came up, right? It is a perfect square. And it's just perfect for our purposes. Look. If you look at this very carefully, you're going to realize, this is z squared plus 1 quantity squared minus z squared. Guess what? That is difference of two squares. So it can be factored into z squared plus 1 plus z multiplied by z squared plus 1 minus z. But guess what? You want to write those in standard form. And when you do, these two factors are going to be the same. Let me rewrite it in a clean format. So this is what I'm talking about. We get this from the first part. And the second part gives us z squared plus z plus 1 and z squared minus z plus 1. Again, this is just amazing. And these are very special polynomials. And you should definitely know how to factor them this way because they always come up on Olympiads and math competitions. If you're preparing for those, this is really a good thing to know. Even if you're not preparing, I think this will help you, with math overall. So now this is our common factor. We're going to go ahead and factor that out. That's a quadratic, which is nice. And then the other one is going to come from here, z cubed minus z squared plus z squared minus z plus 1. We're going to go ahead and simplify this, of course. And at the end, we're going to get z squared plus z plus 1 as the quadratic factor. And the other is going to be z to the third minus z plus 1 equals 0. Now, guess what you're supposed to do at this point, right? You get a quadratic, so that's easy to solve if you use the quadratic formula. Negative b plus minus the square root of b squared minus 4ac. That'll give you that number. And this one is cubic, so we got to be more careful. I'm going to show you what the solutions look like, and I'm also going to indicate how to solve these kinds of things. But this is something that we always see, very common. So make sure to know how to factor these things. That's the lesson here, okay? Now let's go ahead and take a look at how we can solve this cubic. By the way, if you proceeded with the first method, you should get something like this, right? So that kind of gives you an idea if you're lazy, like me, if you don't want to solve the system, but I think it's better if you solve that system. That's definitely going to help you, trust me, okay? Now, to solve this cubic, we're going to be using an identity like this. A plus b quantity cubed minus 3ab, a plus b always gives you a cubed plus b cubed. By naming this as z, we're actually getting a cubic equation whose roots are a plus b, and you can kind of compare that equation to this equation and hopefully find the values of a and b, which you can then cube root, so on and so forth. Let me show you the method roughly, and then you can kind of go take it from there, okay? So this basically means that 3ab is equal to 1, which means ab is equal to 1/3, and a cubed plus b cubed is equal to 1. If you cube both sides, you get a cubed b cubed is equal to 1/27. And then if you isolate b cubed from here, you get 1 minus a cubed. And if you go ahead and take this and plug it in here, that gives you a cubed times 1 minus a cubed equals 1/27. And put everything on the same side, you get something like this, which kind of looks scary because it's kind of like a hexic or hectic equation, right? But guess what? If you set a cubed equal to c, this actually becomes a quadratic, which is very easy to solve with the quadratic formula, which then you can go back to a and b, because those are going to be the cube roots of c, which are real, by the way. Maybe not. And then in this case, I don't think they're going to be real. But you can go ahead and plug them in, find the value of a plus b, which is z, which is going to give you the solutions. At least one solution from the cubic, and then hopefully you can find the other ones. But again, this is way too much work for lazy people like me. We're not going to do it. We're going to use a calculator, ta-da-da-da, do the heavy lifting for us. Take a look at this. Don't you love this, right? This is the real solution. By the way, it's given by the radical expression that I gave you. Wait, did I give you the radical? Anyways, you can figure it out. And these are the complex solutions, and they're beautiful, aren't they? And ta-da-da-da, here's the graph of our function, the quintic, that only intersects the x-axis at a single point, right? And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time in another video. Until then, be safe, take care, and bye-bye.